So today I'm going to talk to you about logarithms. Logarithms are a very important but often forgotten concept that will help you solve lots and lots and lots of problems in math. So the basic idea of logarithms is that we want to solve some equations that might look like this. So e to the x equals 10, for example. What's x? It's not super obvious how to figure that out using a calculator. 2 to the x equals 1024. That one you might be able to solve it by hand if you think about it enough. Or a to the x plus 2 equals 123. And of course you could keep naming more and more complicated examples here, but I just want to show you the basics for right now. So the basic facts about logarithms, the basic formulas we're going to use is that the natural log of e to the x, natural log is denoted by ln here. The natural log of e to the x is just x. So the logarithm undoes this exponentiation operation. Similarly, the logarithm with base b of b to the x is equal to x. So b is usually some constant. For example, say log base 10 of 10 to the x would be x. So we could use this type of formula to solve this equation here or this equation here. So that's a very useful formula also. And finally, there's this thing called the base conversion formula, which is that the log base b of a is the natural log of a divided by the natural log of b. And this thing looks pretty ugly, but the key point is that you can use this formula to evaluate the log with a funny base. So in particular, your calculator might not have a log base b button, but never fear, as long as it's got a natural log button, you can get by just fine using this formula. So all you do is whenever you have to compute a log to some funny base, you compute the natural log of the thing that you wanted to compute, and then you divide it by the natural log of the base. So let me show you how these things work in practice. So I want to solve this first equation, e to the x equals 10. This is about as easy as it gets. You take ln of both sides, so ln of e to the x equals ln of 10. Ln of e to the x is just x, so that tells me that x is ln of 10. And you can't actually simplify ln of 10 by hand. That would be very hard to compute by hand, but a computer makes short work of it. It turns out to be approximately equal to 2.3. So if you needed an exact answer, you could just use this ln of 10 thing. If you need a numerical approximation of the answer, plug this into a calculator and you'll get 2.30 something. All right, so that's the first one. What about this one? 2 to the x equals 1024. So I'll show you a couple methods for solving this. So the first method is to take the logarithm to base 2 of both sides. And that tells me that the logarithm of base 2 of 2 to the x is equal to the logarithm of base 2 of 1024. So that tells me that x is the logarithm with base 2 of 1024. Now your calculator might actually have logarithm to base 2 on it. And that one might not be too hard to enter into a computer either, but if your calculator doesn't, you can of course just do ln of 1024 over ln of 2. That's using this formula right here, the change of base formula. And it turns out that the answer is exactly 10. And if you plug that back into the equation we started with, that makes sense, because 2 to the 10th power is actually exactly equal to 1024. So the second method for solving that same equation is to use the natural log of both sides. So ln of 2 to the x is equal to ln of 1024. And the key trick here is that we have to use one other formula, which is that ln of a to the b power is equal to b times ln of a. And that works no matter what a and b are, as long as the logarithm is defined. So the way that people typically think about this is if you take a logarithm, you're allowed to just take an exponent and bring it out in front of the logarithm. So I just took an exponent from here, and now, bam, it's out here in front of the logarithm. So ln of a to the b is b ln of a. So in this case, that's going to tell me that ln of 2 to the x is x ln of 2. And that's equal to ln of 1024, and therefore x is equal to ln of 1024 all over ln of 2. And that's exactly the same formula that we had previously. It's equal to 10. I'll go ahead and give you a third method if you're comfortable with it, which is that you can actually compute log base 2 of 1024 directly if you're comfortable with logarithms. So the way that you compute this is that log base 2 of 1024 is whatever power of 2 would give you 1024. So you can see by just computing 2 to the 10th power equals 2 times 2 times ... times 2. It turns out to be 1024. if you do this 10 times. All right, so finally we've got one more equation to solve, which is a to the x plus 2 equals 123. So again, I'm just going to take the logarithm of both sides. I'll go ahead and do natural log this time. So ln of a to the x plus 2 equals ln of 123. So then here's my exponent. The logarithm is allowing me to take that out front. So that tells me that x plus 2 times ln of a is equal to ln of 123. So then x plus 2 is equal to ln of 123 divided by ln of a. So then x is equal to ln of 123 divided by ln of a minus 2. And we can't get a numerical approximation in this case because we don't know what a is. A is sort of an unknown constant for us. So if the problem gave us a, then we could go ahead and plug this whole thing into a calculator and figure out what x is, but as it is, we just have to leave it like this. Okay, so those are the basic formulas. Now I want to show you what the logarithm function looks like graphically. So if you're familiar with the exponential function, it looks like this. Y equals e to the x is given by this green curve here. The logarithm function looks pretty much the same but different. So what's going on here is that as x grows negative, the curve really closely approaches the axis. It gets infinitely close to the axis. Same thing with the logarithm, but instead of x growing negative, it's y growing negative. So as y grows negative, the logarithm gets infinitely close to the axis here. And same thing here, as y grows positive, the logarithm grows infinitely quickly. Same as the exponential function, but for x, right? So really what's going on here is that the exponential function and the logarithm function are inverse functions, and therefore the graph of one is given by reflecting the graph of the other one across this dotted red line here, which has the formula y equals x. So that's just a general fact about inverse functions. When an inverse function exists, you can find its graph by reflecting the graph of the original function across the line y equals x. So if you forget exactly what the logarithm looks like, you can compare it to the graph of y equals e to the x, and you can get a really good picture of it that way, and vice versa. But what about other bases? So the most common logarithm bases are e, 2, and 10. E is mostly used in mathematics. 2 would be used commonly in information theory and computer science. 10 would be used in sciences where we're trying to approximate real-world numbers like Avogadro's number or something in chemistry. Probably also in social sciences, you'd most commonly take logarithm to base 10 because 10 is the number system we're most used to working in. So I just wanted to give you an overview of how the graphs of those different bases of the logarithm and exponential compare. So it looks like this. As you could probably figure out by reasoning with it, 10 to the x grows a lot faster than e to the x does. And since e is approximately 2.718281828, e is greater than 2, so 2 to the x grows slower than e to the x does. So I've kind of exaggerated the difference here so that you can actually see these three curves, but 2 to the x in reality is probably going to be pretty close to e to the x. But basically, 2 to the x grows slower than e to the x does, and e to the x grows slower than 10 to the x does. And if you wanted to draw another curve in here, like 5 to the x, it would appear somewhere in here, 5 to the x. And the exponential decay has the opposite effect. Like 2 to the x grows slower than e to the x, but it also decays slower, right? So it's actually bigger than e to the x to the left of the y-axis here. So with the logarithm, you find exactly the opposite behavior because again, these functions are all just the inverses of these functions. So the graphs of the three most common bases for the logarithm function look like this. Logarithm with base 10 grows the slowest. Logarithm with base e, which is also known as the natural logarithm, grows at an intermediate rate, and logarithm to base 2 grows the fastest. And just like for the exponential, they all cross each other at this point on the x-axis, and the growth patterns are reversed thereafter. So just to be clear, if you have a function f of x equals b to the x, that's called an exponential function with base b. So for example, e to the x would have base e. If you have a logarithm, log sub b of x, then that b there is also called the base. All right, so now let's work a little bit more of a complicated example. So in this example, the population of beetles in a terrarium after t months is given by this formula, p of t equals 100 times 2 to the t over 5. And then the problem is asking us to first find the initial population, second find the population after 3 months, And third, find when the population will reach 300 beetles. So we don't actually need logarithms to solve either of the first two parts, but it's worth working these two out just to see how these three quantities end up being related. So first, the initial population. The initial population is given by p of 0. So in that case, that's 100 times 2 to the 0 over 5. And 2 to the 0 over 5 is, of course, 2 to the 0. So that's 100 times 2 to the 0. Anything to the 0 power is just 1. So this whole quantity is just 1. So then this is 100 times 1. So in other words, our initial population is 100 beetles. Okay, so next we want to find the population after 3 months. That's going to be the population at time t equals 3. So we're trying to find p of 3. So plugging that into our formula, p of t equals 100 times 2 to the t over 5, we get p of 3 equals 100 times 2 to the 3 over 5. And 2 to the 3 over 5 is not something that I can compute by hand, so I'm just going to go ahead and use a computer to compute that. And it turns out to be approximately equal to 151.57. But we're talking about beetles here, so it's probably better to round to the nearest whole beetle, since it's unlikely that we're only going to have 0.57 of a beetle walking around in there. So I'll say that the answer is 152 beetles. So the third question is, when will the population reach 300 beetles? So the key thing here is that we don't want to compute p of 300. That tells us the population after 300 months. That's not what we want. So instead, what we need to do is we need to solve 300 equals p of t for t. So substituting in our formula for p of t from the problem statement, we get 300 equals 100 times 2 to the t over 5, right? When we need to find the value of t that solves this equation. So if I divide both sides by 100, I get 3 equals 2 to the t over 5. So if I take the logarithm to base 2 of both sides of this, I get log base 2 of 3 equals log base 2 of 2 to the t over 5. Now, log base 2 of 2 to the t over 5 is just t over 5, right? Because the logarithm cancels out the base of the exponential. So I get t over 5 equals log base 2 of 3. So finally, that tells me that t is equal to 5 times log base 2 of 3, which, by the change of base formula, is 5 times ln of 3 over ln of 2. And now it's finally ready for a calculator. And the calculator tells me that the answer is approximately 7.92. Since t is given in months, that would be in months. If you were asked for an exact answer, then either of these two forms would be fine. And if you only need an approximation, then this would be a good answer for that. All right, so now I just wanted to give you an overview of pretty much all of the important formulas for logarithms in one place. So the first formula, which we didn't actually use up above, is the product rule, which says that the logarithm of a times b is equal to the logarithm of a plus the logarithm of b. So so logarithms are really weird. They turn multiplication into addition. As I understand it, this is actually part of why they were historically first invented, because it's really hard to multiply big numbers on paper by hand. So back in the 1600s, how did they deal with it? Well, they computed the logarithm once, and then they took the logarithm of the product, used this formula, and then all you have to do is add some stuff up, and then you can look up the inverse of the logarithm in a book of tables of the values of the logarithm and exponential functions. But I don't want to give you the wrong impression. This is still a useful formula today. It's just that we didn't happen to use it for any of the problems up above. But this still comes up all the time in math. The second thing is that the logarithm of a to the c is equal to c ln of a. So remember, that's the fact that for a logarithm, we can take an exponent and bring it down in front. That's probably the number one use for the logarithm right there. And a consequence of these two formulas is that the logarithm of a over b is actually equal to the logarithm of a minus the logarithm of b. If you're curious about why that is, you can actually compute the logarithm of a over b in the following way. The logarithm of a over b is equal to ln of a times b to the minus 1 power, and that's equal to ln of a plus ln of b to the minus 1 power, right? That's by this first formula here. And then ln of a plus ln of b to the minus 1 power is equal to ln of a minus ln of b, because I'm allowed to take that power and put it out front. So that's how you can get this formula here from these two formulas here. Okay, moving along, some basic identities. First is that the natural logarithm of e is equal to 1, and in general, the logarithm to base a of the same number a for any a is equal to 1 as well. Also, the logarithms of 1 have a special value, it's 0, so the natural log of 1 is 0, the logarithm to base a of 1 is 0. You can see this on the chart that we drew earlier, right here. So this is that formula, log base a of 1 equals 0, right here, because I'm looking at 1 on the x-axis, so I'm putting 1 into my logarithm, and the height that I get as a result of that is 0. So log base a of 1 is 0 for any base a. Next, there's the change of base formula, which is that the logarithm to the base b of x is equal to ln of x over ln of b. And actually, you can do this change of base using any logarithm. Natural log isn't actually special. So logarithm to the base b of x is also equal to log base a of x over log base a of b for any a which is greater than 0. Not just a equals e, which gives you this formula here. So the next important property is the first one we covered, which is that the logarithm is the inverse of the exponential function. So log base b of b to the x cancels out the exponential, and you're ending up with just what was in the exponent. So log base b of b to the x is equal to x. Next, natural log ln is defined to be the logarithm to base e. And finally, I just wanted to note one other important property of logarithms, although there's a few others that we won't have time for right now. But the property I wanted to note right now is that logarithms preserve inequalities. The same is true of the exponential function, incidentally. So what do I mean by that? I mean that if I have two functions, f and g, and f is greater than or equal to g, then the logarithm of f is actually greater than or equal to the logarithm of g. So that's really handy. That's one of the reasons that logarithms are very useful, because they preserve the relations between functions. If you have one function that's always bigger than the other one, but it's hard to graph them both using computer graphing software, for example. You can just take the logarithm of both of those and graph it, and your graph will become much more compact. But you'll still be able to see the relationship of both functions, which one's bigger than the other one, where they cross, etc. And so this isn't special with just the greater than or equal to. It also preserves less than or equal to. If you think about it, that has to be the case if it preserves greater than or equal to. But just so it's stated explicitly, if f is less than or equal to g, then the logarithm of f is less than or equal to the logarithm of g, and vice versa. Finally, I just wanted to also mention sometimes people write log of x to mean ln of x, or log base 2 of x, or log base 10 of x. You kind of just have to figure it out from the context. So most commonly, I think if somebody writes log of x, they mean ln of x. It's just a matter of notation. If you don't specify a base, the base is supposed to be clear from the context. All right, so I'll just leave it there for today. Thanks for listening, and have a nice day. Good luck with logarithms.